hours, or really 2 hours and 50 minutes to complete the final. All right, the final is mostly multiple choice. All right, there are going to be 35 questions in total on the final, and 31 of them will be multiple choice. So what you can expect is it's a very different format from what we're used to in exams. And one of the things that I thought would be worthwhile to do both today and next Monday is to take some time to talk about these different this format, and look at some questions and some strategies that you might use to deal with this multiple choice format, which is something, again, it's new. Now, the way it's going to work is you're going to have an answer sheet. All right. I've decided against using the Scantrons. I just detest the things. And so I've made up my own answer sheet using a different app. The whole spacing of it is a little bit larger than what you see in a standard Scantron. And the other thing is I can scan it with my phone. All right. The 4 non-multiple choice questions will cover 2 topics: titration curves and buffers. All right, so you think about the problems that you've seen already on those. And I do have some practice problems included with what we're going to be doing over the next couple of class periods. All right, so here's what I want you to do. We're just going to practice some of these questions and talk about this. So the easiest thing for you to do is to log into this either using your phone or on your computer. It'll work either way. All right. You go to the website Socrative.com. You don't have to log in. Okay, all you have to do is enter as a student, and then you just go to this room, Y17PFPLH. Right? Now, I'm not going to grade you on any of the participation today, although I do encourage you to participate because I think it's helpful. All right? But what we're going to do is we're just going to look at a whole bunch of questions using this app. All right, and basically it's just a bunch of multiple choice questions, at least to start, although I did throw in a few questions along the lines of the latter ones at the end. Now, one other thing I should mention about the final is there are 35 questions. It's 3 points per question. So if you got a perfect paper on the final, you would get 105. And everybody in the department is perfectly okay with that. I've actually never seen it happen, but others have. All right, so it is conceivably possible to get a perfect paper. All right, it's challenging though. There's a lot of material that you have to go back and review, and that's actually what we're going to really focus on this morning, or this afternoon rather, is just talking about some of the earlier chapters. You also might want to go back and take a look. I did put together some course outline videos that I recorded several years ago. And you might want to look at those, just where I outline some of the more important ideas from each chapter. All right, so let's go into Chrome. And sorry about the dazzle there. Come on. All right. So what you're going to do is you're going to launch Socrative, and then once you do that, you're going to start seeing questions once I pull them up here. All right. And what I'm also going to do is I'm going to scramble the answers in the questions. All right. And you can put your name in if you want. That's not necessary. Let's shuffle the answers though. And what we're going to do is we're going to do teacher paste because I'm going to go through it. What we'll do is I'm going to take some time, let you answer each question, and then we'll go over the question as well and some things that you might look for with these things. One of the distinct advantages of a multiple choice exam is that you have, or that the correct answer is staring at you off of the page. All right. One of the things that you can think about is how do you identify that? All right, so far I see only 2 people on. The rest of you should get on. All right. Even again, I'm not going to grade you or anything like that for participation, but I think it's definitely in your best interest to get on this. So please do. All right. Again, the room number is up here. Y17PFPLH. Okay, that's better. Now we're up to 5. That's good. All right. So let's take a look at this first question, and you can go ahead and start answering these things. But now we're down to 4. All right. Whoops. So again, the answers might appear on your device a little bit differently than they do here. And one other thing you can think about, and this will be true with regard to the final as well as what I do here, is I'm going to cover material, and the final will cover material in the order in which it was covered in the course. So what you can expect is that the first questions on the final will be from chapter 11. And then you could work through from there. Now, some people, because of that, they choose to work backwards. They start with question number 31, which would be chapter 19, and then work back to these other questions. All right, that's a matter of your choice. You can do it however you like. You just need to make sure you answer everything. And it definitely is in your best interest to answer everything. You're not going to be penalized for getting wrong answers. All right, so far we've only got one answer for this. Take another minute and see what you can do with it. So, if something is a gas at room temperature and room pressure, what does that suggest about it? Is it going to have strong intermolecular forces or weak intermolecular forces? Yeah. Okay. So, what we're thinking about here is we're thinking about a substance that has the weakest intermolecular forces. Okay, so really what we're looking for then is if you think about the intermolecular forces we talked about, which are dispersion forces, dipole-dipole interactions, and hydrogen bonds. The first thing we want to think about is, okay, we want to look at things that only have dispersion forces, molecules that are non-polar, in other words. Okay, now there's another trick to this problem, and that is that not every compound that's listed here is molecular. Which compound is definitely not molecular? What do you think? I2 is molecular. Think about the other types of compounds that we talked about. Okay, we talked about and we talked about them in the context of solids. Okay, remember we said there are 4 types of solids. Molecular compounds make up one of those 4 types of solids. We had covalent network solids, we had ionic solids, and we had metallic solids. Any of these compounds fit any of these other categories? What do you think? How did we learn back in Gen Chem 1 to identify an ionic compound? What did we do? Nobody remembers that? What did we do? How did we identify ionic compounds? They have a metal in their formula. Okay, and we can see the very first possible choice, calcium oxide, has a metal in its formula. All right. We can see, so, and the other thing we can think about is if we look at antimony trichloride, that's probably also an ionic compound. If nothing else, it's going to have a dipole moment because chlorine is very electronegative. So I'm going to scratch that one. That leaves us with three possibilities. And if we look at all three of these possibilities, we would come to the same conclusion that they all exhibit dispersion forces as their strongest intermolecular force. All right, so we've gotten down to that criterion. How do we decide if dispersion forces are dominant, where they're going to be weakest? What do we do? If dispersion forces are the dominant intermolecular force between a molecule, then how do I judge which one of these three possibilities is going to have the lowest melting point? I would have to look at molar masses. All right, so really what I'm doing is once I've chosen that the dispersion forces is what I'm looking for, the next thing I'm going to do is I'm going to say, okay, which of the molecules that are left have the lowest molar mass? And what's the answer to that? Is it I2? Is it SiH4? Or is it C8H18? Ah, yes, C8H18 does probably have the, actually, I think I2 might be higher. Okay, here's what I know. At room temperature, I2 is a solid, okay? C8H18 is a liquid. All right, it's octane. It's what we use as a rating for gasoline in terms of its combustibility, okay? And so what that leaves us with is this one. And indeed, if you look at the molar masses, the silane, as it's called, or silicon tetrahydride, if you prefer, is the lowest molar mass. So it's most likely to exist as a gas at room temperature, and indeed it does. Let's see, how did we do on this one? Yeah, okay. All right, kind of a mixed bag all over the place. These are definitely things that you want to recall for next Wednesday. All right, let's move on to the next question. Let's see, where are we? All right, so this is kind of the same idea as the last one. Okay, but it takes into account one other intermolecular force that was not covered in the last problem. Which of the 5 substances listed are going to exhibit hydrogen bonding? Anybody want to stick their necks out on that one? How do we identify if hydrogen bonding is going to exist between molecules of a substance? Hydrogen has to be bound directly to what 3 elements? Nitrogen. Yep, oxygen is one. And what's the third one? Right next to oxygen on the other side. Yeah. All right. So what do we see here? We see water, hydrogen bonding. We see hydrogen fluoride, hydrogen bonding. All these other substances have a dipole moment, but the dipole moment probably isn't as much of an effect as molar mass. And so, based on molar mass alone, what we would conclude is that HCl probably has the lowest boiling point of the remaining three substances. And indeed, if I can bring up my cursor, there we go. Yeah, that's the correct answer. All right. So these are the kinds of things, again, you want to think about this a little bit. All right, here's another problem you're definitely going to see a type of. What do we need in order to solve this problem? What do you need? It involves sorry, go ahead. We need R value. Okay, but what equation are we going to use here? Yes, we definitely need the R value. So we're going to use that Clausius-Clapeyron equation. Now, here's something you want to think about with the final. I told you for your exam you needed to remember the Clausius-Clapeyron equation, and perhaps you still do. All right? But if you flip to the very last pages of the final exam, you will find an equation sheet. Now, the problem is on that equation sheet, there are at least three distinct forms of the Clausius-Clapeyron equation. Any of them will work, all right? The one that we learned to use was this one. The natural log of the vapor pressure ratio at two different temperatures is equal to negative delta H of vaporization divided by R, and then times 1 over T2 minus 1 over T1. Now, if you go looking on that equation sheet, you're going to find at least two other forms that are listed there. Again, they all work. They're all the same thing. They've just been rearranged a little bit. All right. The other thing you're going to find in the information sheet are several R values. You're going to see that R is equal to 0.0821 liters times atmospheres over moles times Kelvin, or we have that value of R. Which one are we going to use here? We're going to use 0.0821, or are we going to use 8.314? Yeah, that's the one we want to choose. All right. So write that down. Take a few minutes to work it, and then we'll go over it and see what you can think. Now, the other thing you can think about with problems such as this one is, are there answers that don't make any sense? Okay. Now, let's look at this carefully and think about that, because a lot of times it has relevance. It's probably not so much here. Here we have a compound with a heat of vaporization of about 30 kilojoules per mole. Okay. Now, if the compound has a vapor pressure of 111 torr at 274 K, what would we expect for the vapor pressure at 311? Is it going to go down or is it going to go up? If you increase temperature, what always happens to vapor pressure? It goes up as well. Yeah, we would. So by that, we can cross out one answer right away, because there's no way the vapor pressure is going down. Now, there's another one where the same thing is true down here. I would say there's the third one as well, because if a heat of vaporization is around 30 kilojoules per mole, every 10 degrees you raise the temperature is going to cause the vapor pressure to go up by a factor of about 0.7 or so. Right? So roughly every 15 degrees, you would expect the vapor pressure to double. And here we're talking about raising the temperature almost 40 degrees. And so that eliminates that choice as well. So really, just by doing no math and just thinking about this a little bit, what we can do is eliminate at least two answers, and this third one as well, I think. So see what you come up with from the remaining two. So if I do the math, I get this. The natural log of the ratio of P2 to P1 is 1.56. How do I get rid of that natural log term again? Yeah, so if I want to calculate the ratio of P2 to P1, what I'm going to do is take E raised to the 1.56 power. And if I do that, I get 4.75. And so what that tells me is at 311 kelvins, my vapor pressure should be 4.75 times what it was at 274 kelvins. So there's only one answer that fits. It's going to be this one. Right? The others are too small. So how did we do with that one? Whoops. Okay, not bad. Not bad. So here's one of the things that you want to think about with problems like this. Even if you're not completely sure about how to finish the problem, what you might want to think about is, well, can I use the logic that I have learned to come to the right answer? And the answer for a lot of these questions is you can. You don't have to go through every last little bit of math to get the right answer. You may want to do that to double check things, but in some cases you can just think things through and look at them. Okay, so but the one thing that's missing from this practice final that you definitely should think about as well is the whole idea of solids. There were two things we looked at in terms of solids. One was identifying crystalline solids and identifying them from their properties. That has sometimes appeared on the final. And the other one is relating density and side length for cubic lattices, for both face-centered and body-centered cubic lattices involving metals. That's another thing that has a reputation to appear on the final. All right, I just didn't have time to put questions in here. But you can look at the review sheet for chapter 11 and see a question along the lines of what I've just described. It's the last question on the review sheet. All right, and I did post those. All right, but now we're moving into chapter 13, which involves solutions. And basically what what this question is asking me is, if I have a 26% solution of glucose, what mass of that solution contains 44 grams of glucose? So see what you can do with that. And this is another one. If you think about it, there's only one answer that makes sense. First thing you want to ask yourselves is, if I have a 26% solution, right, what does that mean? What is a 26% solution? It means that if I have 100 grams of solution, I have 26 grams of glucose. So if that's true, would I expect more solution to have more glucose, or less solution to have more, or this amount of glucose? There are several ways you could set this up. One of the easiest ways is to set up a proportion, and you say, all right, I'm looking for 44 grams of glucose. And what mass of solution? All right. But here's what I can tell you. I need 100 grams of solution to deliver 26 grams of glucose. That means I need more than 100 grams of solution to deliver 44 grams of glucose. Look at your answers. I don't have to do anything more other than that, because that one's less, that one's less, that one's less, and that one's less. Leads you to the right answer. Okay? I didn't have to do any math. All I had to know was I need more solution. So again, think about those things. All right? And look at them. And again, it's definitely in your best interest to participate in this, because even, I'm not going to embarrass anybody by answering questions incorrectly or anything like that. But I do think it's going to help you to understand how to do these problems and get ready for that with regard to the final. Okay, here's another classic question that appears. And you want to read this carefully. Take about a minute. I want to see 7 answers in a minute, please. See what you can do with it. Just stick your neck out. And again, this is another one where if you think about this and you read it carefully, you can answer it without having to do any real calculations. If I say something is 2.7 molal, what does that mean? What is the definition of molality? Moles of solute per kilogram of solvent. Exactly. So if I have a 2.7 molal solution, that means I have 2.7 moles of urea in 1 kilogram or 1,000 milligram, or excuse me, 1,000 grams of H2O. So how many moles of glucose would I have to dissolve in water to make a tenth as much solution? There's the answer. 1/10 as many moles. I don't need the molar mass or anything like that. All right, that's a trick. And sometimes you see that in these questions. All right, sometimes extra information is given in the question that you don't actually need to solve it. And you want to think about that. You know, how do I map myself out so that I solve this question? Those kinds of things. That's important. All right. How did we do on this one? Whoops. All right, next question. Which would we expect to be the least soluble in water of the compounds listed? What's the general rule of thumb for solubility? Does like dissolve unlike, or does like dissolve like? What do you think? Does like dissolve like, or like dissolve unlike? What do you think? What is the strongest intermolecular force between water molecules? Yes, hydrogen bonding. Okay, so these are all molecular substances. All right, we don't have any ionic substances in here. So what we want to do is we want to go through each of these examples and see which of them have hydrogen bonding between their molecules, because those are probably the most likely to be water soluble. Does the first substance have hydrogen bonding between it? It contains fluorine, but is the fluorine directly bound to hydrogen? No. All right, so let's put a question mark by that one. If I can get this thing to draw. There we go. We'll put a question mark there. All right. What about the next one? What do we see that might show hydrogen bonding? We see this NH2 group here at the end of it. Okay, so there, that one has hydrogen bonding. The third one, we see an OH group in the middle. That suggests hydrogen bonding. And the fourth one, we have the OH group here. The fifth one, we have an NH group. So all of these, except for the first one, have some form of hydrogen bonding to them. And so what that suggests is the first one, even though carbon-fluorine bond is polar, this molecule probably won't dissolve in water very easily. All right, so how did we do with that? Yep, all over the place. Okay. But yeah, like, remember the general rule is that like dissolves like. And that's how you have to approach a problem like this. Look for something with hydrogen bonding between its molecules. Okay. So, take a few minutes to work this. How do I figure out mole fraction? That's something you definitely want to be prepared to do on the final. We talked about the definition of mole fraction, and we had one application of it in chapter 13 with regard to vapor pressure of solutions. Okay, but what you want to think about here and is what is that what is mole fraction? How do you figure it out? How could you define 35%? There are a bunch of ways to do it. The easiest one is to say, all right, if I have a 35% solution, that means I have 35 grams of water per 100 grams of solution. All right? Or another way of thinking about this is 35 grams of water. The remainder of the mass of the solution is ethanol. So that's 65 grams of ethanol. What's the definition of mole fraction? That's something you definitely want to know for the final. If I want to figure out the mole fraction of water, how do I do it? Something divided by something. That's implied in the word fraction. What is a mole fraction? In this case, it would be moles of water divided by the total moles in the solution. So we need to know moles both of water and of ethanol. So if we have 35 grams of water in this solution, divide by the molar mass of water, all right, and then we can do the same with ethanol. We have 65 grams of ethanol. All right, So we have 1.94 moles of water and 1.41 moles of ethanol. Does that mean the mole fraction of water is going to be greater than 0.5 or less than 0.5? Which one? Is it going to be less? Are you sure about that? Think about this. How do we figure out the mole fraction? We're going to take 1.91 moles of water, and we're going to divide that by the sum of 1.91 and 1.41. Or excuse me, 1.94, excuse me. 1.94 and 1.41. Clean it up a little bit. Yeah. All right. But my point is, if I just look at this, I'm dividing 1.94 by a number that's not twice as great as 1.94. Therefore, my mole fraction has to be greater than 0.5. Without doing any more, I can scratch 3 answers. All right. And so, yes, as was said, that leaves us with, if we actually carry this out, it's going to be 0.58. Yeah, of course, there's only one person or 3 people answered it. All right, what about the rest of you? There's 7 people on here right now, at least. I think there are even more than that. You don't participate, you're not going to get very much out of this. So you definitely should participate. All right. Here we go. This is definitely something you want to be able to do for the final as well. Change from molarity or density to percent in density to molarity or to molality. Something we covered on the first exam as well. How do I go about doing this? Take a couple of minutes to look at this and see if you can figure it out. I want to see everybody answering it too, please. Don't just sit there and expect and not participate in this. You're not going to get very much out of that if you do. There's one answer here I can eliminate straight away. It's just too large. 60 moles of HCl in a liter solution. I don't think that's going to happen. Nobody else is going to answer this? We got 3 people. Am I going to have to create a participation an assignment for this today? Okay, there we go. That's better. Now we're up to 7 out of 8. That's pretty good. All right, so what are we going to do? We figure out again, if we're going from percent to molarity, that means we want to say, okay, how much solute and then the amount of solution. If it were to molality, we would use the other one like we did looking in the previous example. All right, where we'd say, okay, it's 19.9 grams for so many grams of water. All right, but for molarity, we want moles of HCl per liter of solution. So what we're going to do is we're going to multiply this by the density, and then we're going to multiply by 1,000. That's going to give us moles per liter. Now, this one is a bit more challenging because there's this answer here. And again, I can eliminate that. I don't think there are any examples of a 60 molar solution. You can't have 60 molar solution of water because only 55.5 moles of water are in a liter. Okay, it doesn't work. So you have to think about things like that. All right. So, what's my answer? Let's see what the survey says. Okay, most of you got it correct. That's good. It's 6.0 molar. All right. These other answers are so close, and everybody chose answers that are close and would be reasonable just given everything. But again, you've got to make sure you can do those calculations. And I would definitely advise you take some time to practice that one as you approach next Wednesday. All right. Now we're going to move into chapter 14, which has to do with kinetics. So, which of the following would not affect the rate of a chemical reaction? Take a minute to answer it. I want to see 8 answers, please. So get all your answers in and think about it. Again, you can think about what factors influence a rate of reaction that we talked about at the very beginning of the chapter. Take about another 30 seconds on this. So we got 3 people still holding out. Get your answers in, please. So, does adding more reactants affect the rate of a chemical reaction? What do you think? If you increase the concentration of reactants, that's kind of another crude way of thinking about this. Is that going to increase the rate of a chemical reaction? I'd say so. Removing products. Think about, what does the rate law for a chemical reaction look like? It's proportional to the concentration of the reactants raised to certain powers. but it has nothing to do with the products. So that's a possibility. Okay? Increasing the temperature. We know changing the temperature affects the rate of a reaction. Decreasing the temperature, same thing. Okay? We also know that adding a catalyst. So again, there's our logical answer. That's it. All right, a catalyst always speeds up a reaction. That's the definition of a catalyst. So you definitely want to remember that as well. All right. Here's another one we covered in class, but here again you can think about it in terms of just the answer being there. Okay. How many times faster does I2 form compared to IO3 minus disappearing? That's all you have to think about here. All right, it's not that complex. And essentially what you can say is the rate of formation. You're given this. You're told, okay, the rate of disappearance of iodate is 2.8 times 10 to the negative third. That's molar per second. Now, that's the rate of disappearance. Okay, remember, when a reactant disappears, you have to put that negative sign in front of it. What's the relationship between the rate of formation of I minus and the rate of disappearance of IO3? Is it the same? The answer is no. It's not the same because of the coefficient here. For every 1 mole of iodate that disappears, I'm going to form 3 moles of iodide, or of I2, not iodide. All right, and so I've got to pay attention to that. All right, so the rate of appearance is going to be 3 times the rate of disappearance, and the sign's always going to be positive. And so that means it's got to be choice, at least on the way it appears here, it would have to be choice C. All right, almost everybody got that. And the other answer is about the closest to reasonable as you can get otherwise. So that's good. All right. So we have to remember our rate law units. If we have a second order reaction, what are the possible units of the rate constant? Take about a minute to answer that one. Again, I want to see 8 because we got 8 people on here. It's better to guess and be wrong than not to guess at all. And that's something you want to think about with the final as well. You make a guess, you got a 1 in 4 or 1 in 5 chance. Okay, and here in this case, you got a 1 in 4 chance. All right, but you can think about this a little bit more as well, and maybe come to some better conclusions. What does this second order rate law look like? Yeah, okay. That's correct. Because the second order rate law is going to look something like this. All right. And if your rate is in units of molar per second, then the units of K are going to be reciprocal molar, reciprocal second. Now, that particular unit isn't there, but what's closest to it? Reciprocal molar, you could write like this, liters per mole. And so that fits this one here. All right. So again, you want to remember your units for rate constants. It comes in handy not only to answer questions like this, but sometimes questions are phrased in such a way that they don't actually give you the rate law. They just give you the units for the rate constant. Okay, so here's another kinetics. Tungsten 188 decays by first order with rate constant of 1 times 10 to the negative 2 reciprocal days. How long will it take for 93% of the initial amount to be consumed? That means that at that particular time, 7% is left. All right, there was a question like this on the second exam that a lot of you had trouble understanding, and again, these are kinds of questions that you'll see on the final. So you might want to think about this and make sure you understand exactly what's going on here. Now, the other thing again is you need to remember some things. We're talking about first order kinetics here. One of the things that we talked about with regard to first and second order decompositions were these integrated rate laws that we used. And again, you don't have to remember them, but you have to recognize them and be able to use them. For a first order reaction, there are 2 forms of the integrated rate law. The one that I taught you to use most is this one. The natural log of a constant of whatever component it is at time t is equal to negative kt plus the natural log of the starting concentration, or in this particular case, you could throw amounts in there. All right. You could also, and again, you'll see this form of this equation in the back of the exam. Right, there's another one that you could just as easily use, which is this one. The natural log of the ratio of the concentration at time t with respect to the starting concentration. It's just rearranging the equation on top is equal to negative k times t. Right, they'll both work for this. So there are two ways to approach this. This is one. All right. If I do this, at least according to my calculations, I get 265 days. And so the closest answer is choice D. All right. Another possibility that you could try with this is you could say, all right, what's the half-life of this? Okay, this is another equation that you'll see in the back of the exam, and that is the half-life. 0.693 is equal to the rate constant times the half-life time for a reaction. So if you do that, I take 0.693 and I divide it by 1 times 10 to the negative 2, I get 69.3 days. All right, so that means if I start with a sample of tungsten 188, after 69.3 days, or roughly 70 days, I'm going to be down to 50%. After another 70 days, or say 140 days, or really 138 days, I'm going to be down to 25%. Okay, so thinking about that, that scratches that one, that scratches that one, scratches that one. All right, 2 half-lives, I'm down to 25%. After 3 half-lives, which would be about 210 days, I am down to, what would it be? 12.5%. Okay, so again, I'm still not at that 7%. So the only answer that makes any sense is 270 days. So you see there's several ways you could figure this out with the information that you have. It's just a matter of what you choose to do. In both cases, though, you have to remember that we're talking about integrated first order kinetics. All right. Here is a problem that we have mentioned briefly, but what you want to think about is, again, I don't think we actually talked directly about getting the correct answer to this problem, but you can get to the correct answer by process of elimination if you remember some of the other things that we talked about. We've got a reaction profile. It's shown in the upper right of this screen. All right. Basically, what you want to do is you want to choose the correct statement. And so what you can do is go through and say, all right, which of these statements are incorrect and which ones can I cross out because they are incorrect? So see what you can do with that for a few minutes. Look at it. Okay, try to cross out or to eliminate the incorrect answers. Get your answers in. Let's look at this. Given the profile that's shown over here on the upper right, is this reaction exothermic or endothermic? Yeah, it's exothermic. So that means we can cross off the first one because the forward reaction is not endothermic. Okay. Is the activation energy for the forward reaction greater than it is for the reverse reaction? Here's the activation energy for the forward reaction. Here's the activation energy for the reverse reaction. Is the forward reaction have a greater activation energy than the reverse? No. Okay, so we can cross that one out. Is the activation energy for the reverse reaction negative? What does this show here? It shows that the activation energy for the reverse reaction is positive. So no. Okay, so we've eliminated 3 choices. Again, we don't know what the answer is. All right. The effect of temperature change is greater for the reverse reaction than the forward reaction. All right, there's nothing that tells us that directly from this, although we can see actually that it is true. All right, so we put a question mark by that. Let's go to the last one. A and B are more stable than C and D. Well, C and D are lower in energy, so they're more stable. So that's not true. Okay, so even though we haven't talked directly about this, actually, I think we did very briefly. Okay, because I always remember this question when I present this because I've been doing it for so many years. All right. But the truth is, what you can think about, given the Arrhenius equation that relates temperature to activation energy, the bigger the activation energy, the more effect the temperature is going to have on the rate of a reaction. Okay, that's basically one of the things that we get from the Arrhenius equation. And it's true here. The reverse reaction has a larger activation energy than the forward reaction. Because of that, if I increase the temperature, there's going to be a disproportionate increase on the rate of the reverse reaction versus that of the forward reaction. That's another reason that exothermic equilibria get pushed to the left when you increase temperature, because of that disparate effect on activation energies of forward and reverse reactions. All right, so that is your correct answer as a result. All right, and again, what you need to think about is just being able to interpret these reaction profiles. That's something you definitely want to be able to do. Okay, now we're going to move into chapter 15 when we talk about equilibria. And notice something, and this is something I think you can think about as well on the final, is there's nothing on mechanisms from chapter 14. So that's something else to think about. Okay. Which of the following values of an equilibrium constant does the reaction mixture contain essentially products? This is an easy question. Okay, and you're going to find questions like this. Don't be alarmed that it seems so easy, because it is. If products are favored in an equilibrium, is an equilibrium constant going to be large or small? What do you think? If products are favored, large or small equilibrium constant? Anybody want to stick their neck out for that one? Is it small? Well, think about it this way. Say you have this reaction. Let's write it out. A plus B in equilibrium with C plus D. Which goes on the top of the mass action expression? If I write an equilibrium for this, then I'm going to have C times D on the reactant, or on the top, and I'm going to have the reactants on the bottom. So if the products are favored, what do we see? We see that this part of the equilibrium constant is going to be large. So it's going to be very large, right? There's your answer. All right. Yeah, got to remember that. If it's 10 to the 0, that means you have equal concentrations on both sides. And of course, if it's really small, then you're going to have mostly reactants and not much in the way of products. And again, you can see, based on some of the stuff that we did later in the semester, that you can have really, really large equilibrium constants depending on the circumstances of things. Okay, what do you do with this one? We have a reaction where the equilibrium constant is 1.4 times 10 to the fifth. And what we want to think about is, how do we relate the second equilibrium to the first? And then how do we calculate the equilibrium constant for that? Do we flip it or do we multiply it by 2 or divide by 2? That's correct. And there are 2 in the first. So that means we're going to divide by 2, right? At least you can see the factor 2. That's good. So how do we deal with that in terms of equilibrium constants? What we say is this. If we're going to flip a reaction, that means we're going to take 1 over 1.4 times 10 to the 5th. Okay? If we have the coefficients, what do? We take the square root. Okay, so we're going to take the square root of 1 over 1.4 times 10 to the 5th, or another way of writing it is 1 over the square root of 1.4 times 10 to the 5th. Either way, you're going to get the same thing. It has to be fairly small. Okay, it's definitely not going to be A. It's not going to be the same or the reciprocal. Okay, it's going to be the square root of the reciprocal, and the only one that fits that is this. Okay, this is 2 times 1.4 times 10 to the negative, or 10 to the 5th, and this one, I don't know where they got that one from. So there's really only one possibility. And indeed, that's what we got. Okay. All right, we got one more question on this set. In this particular case, we've got an equilibrium. The Kc is given as 4.0 at 228 degrees Celsius. This one you've got to read a little bit carefully, okay? Pure PCl5 is added to the reaction system. At equilibrium, there is 0.16 molar PCl5. What is the concentration of PCl3 in this system? All right, so let's write some stuff down here. These are all gases, so I'm just going to leave them as gases. All right, but the PCl3 or 5 decomposes into PCl3 and elemental chlorine. All right, if we write an equilibrium constant for this, that means we have the concentration of PCl3 and the concentration of Cl2 in the numerator and the concentration of PCl5 in the denominator, in the denominator. All right. So, what we want to think about is we know the value of the equilibrium constant. We know the amount of PCl5 in the system at equilibrium. And we also know this to be true. If we start with pure PCl5, then at equilibrium, the concentration of PCl3 has to be equal to the concentration of Cl2. For those of you who are in lab, this is something we've done twice with solubility product equilibria. We said, okay, if we can determine one of the concentrations at equilibrium, we can know that the other one is the same because they both come from the same place. Okay, they both come from the equilibrium itself. So in this particular case, what we could say is that the value of the equilibrium constant, which is 4.0, is equal to the concentration of the two components, which are both the same, divided by the equilibrium concentration of the PCl5. We don't really need to set up an ice table in the same way, okay, because we're not given initial amounts or anything like that. All we're told is, okay, we start with a certain amount of PCl5, we let it come to equilibrium, we measure its concentration, we can figure out the other concentrations from that. And so that means if we do this, take the square root of 4 divided by 0.16. How can that be right? All right, there's something not right about this. Because if I do the math, I get 5. Is that what you're getting? Yeah, so the answer's not here, is it? All right, let's see. What are we doing wrong? Nothing. Huh. Yeah, I get 5. What does it say the correct answer is? You got 0.8. Okay, what did you do different? Oh, I'm sorry. That's my mistake. I'm dividing both sides by 0.16. Yeah, I see what you're doing. Yeah. All right. So, it's 4 times 0.16. That's it. Yeah, that makes more sense. And then take the square root. So 0.8. All right. So we do have a correct answer. Yep. All right. One more question from this one. And then let's see where we are. Oh, that's it. Okay. Let's finish that one. I'm not going to go through the reports. I don't think that tells me anything. Let's see. Let's go back and do another one. So what we're going to do is we're going to start the second one. There are 2 sets of questions in here. Let's see. There it is. Final review 2. Let's do it the same way we did the last one. Shuffle answers. All right. All right, this has a lot more questions on it. So now we're going to move into chapter 15, where we talked about acids and bases. All right, so here we've got a solution of perchloric acid. Huh, that's interesting. It looks like a lot of you got kicked out. Or did a lot of you just leave? No. Interesting. Okay. So, what happens when a solution like this, or when you have a solution like this? And what you have to think about is what kind of solution is this? Go back to what we described in class itself when we were talking about these solutions. What kind of solution do we have here if we have a solution of perchloric acid? Is it a strong acid solution or is it a weak acid solution? It's a strong acid, yeah. And so what do we say about strong acid? Do they completely dissociate or not? They do, exactly. And so what you can think about is if you write this out, chemical formula of perchloric acid is HClO4. You bring this into solution, and actually it's considered to be the strongest of the strong acids. What's going to happen to it is it's going to behave entirely like an ionic compound. And so the only components you're going to have from the dissociation of perchloric acid are hydrogen ion or hydronium ion if you prefer. That's not the context of this particular problem, but it could be on your final, and the conjugate base. If this were a weak acid, then you would look for conjugate acid, hydrogen ion, or hydronium ion, and conjugate base. But for a strong acid, it's only going to be hydrogen ion and conjugate base. And that's it. All right, so that's something you want to remember. All right. The other answer that people chose is reasonable if perchloric acid were a weak acid. Okay, for a strong acid, it doesn't fit, but for a weak acid, it does. So if you were talking about chlorous acid or something like that, then that answer would definitely fit. Okay, next question. What's the conjugate base of this anion? And think about how we defined that before. What makes a conjugate base or a conjugate acid? Conjugate base. This is an anion, but the conjugate base is the form of this anion that, it's H2PO4, where I take away one more proton. So what I'm going to end up with is this anion here, this monohydrogen phosphate anion, if you will. That's what it's known as in the trade. All right, and so what did we get here? We got, okay, everybody chose it. Good. Okay, here's a challenging question. How do we define a Lewis base? What is the definition of a Lewis base? Is a Lewis base an electron pair donor, or is it an electron pair acceptor? Ah, which one? It is a donor. All right, think about ammonia. All right, we know ammonia is a base in and of its own right using the Arrhenius definition. All right, why is it an Arrhenius base? Why is it a Bronsted-Lowry base? Because it has a pair of electrons that can donate into a proton. All right, so essentially, if we want something that's a Lewis base, we want something that's an electron pair donor. We want something that's electron rich. Which of these is going to be the most electron rich? Go ahead. What do you think? The only one I can eliminate, given that, is this. Aluminum is not a good Lewis base. Aluminum ion is a good Lewis acid. It's electron deficient. Okay? All these others are Lewis bases, but which one's going to be able to give up electrons the most easily? The one with the most negative charge. Yeah, exactly. All right. If I look at 3 of these answers, this one down here, this one here, and this one here, these are all going to be Lewis bases. But the more electron rich they are, the more charge they have on them, the more likely they are to be Lewis bases. And so what you would argue here is essentially what you can think about in this case is we have a progression of conjugate bases or conjugate acids, depending on the way you look at it. Okay, hydrogen sulfide is the conjugate acid. The sulfide or the hydrogen sulfide anion is the intermediate, and the sulfide anion is the farthest conjugate base. It's going to be most able to give up a pair of electrons because of that, because it's proton deficient. All right, so your correct answer would be the sulfide ion. All right, and this is what you can think about with problems such as this. Just remember, what is a Lewis acid and what is a Lewis base? A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. If something's an electron pair acceptor, it's going to have a positive charge. Okay. So of this list, aluminum would definitely be the strongest Lewis acid. Water is a decent Lewis base as well, but hydrogen sulfide's even better because the sulfur has a lower electronegativity. Okay, now you need to think about what does pH, how do we define pH? And what is equivalent to that? We talked about a number of these, but some of them you have to think about a little bit more. How did we define pH? Which of the answers matches our definition of pH that we used in chapter 15? What does pH mean? Anybody would stick their head out, or their neck out, rather. What is the definition of pH? What did we use to define pH? How do you calculate a pH on your calculator? Yeah. Okay. So there's one answer we can eliminate right off the bat, okay? Because we learned how to calculate pH by taking the negative log. So that answer's gone. Okay? Are there other answers that represent the same thing in different terms? Yes. 14 minus POH. Okay, that was another way we learned how to calculate pH, right? All right. What about log of 1 over hydrogen ion concentration? Isn't that the same as negative log? Okay, try it on your calculators to prove it. Take the negative log of 0.10 and then take the log of 1 over 1.1 or 0.10, excuse me. Give you the same thing. Okay, so that eliminates 3 possibilities. What about negative log of Kw divided by the hydroxide ion concentration? Remember that Kw, get my pen right, is the product of the hydrogen ion concentration and the hydroxide ion concentration in any aqueous solution. All right, so does that work? Yeah, it does. Take Kw divided by the hydroxide ion concentration. That's going to give you the hydrogen ion concentration. All right. If you look at the bottom one, we learn to define this as pKw, which we said was 14. So there's your correct answer. All right, now it would be another way of defining it as well, or of looking for it, is to say, okay, negative log Kw. That's not pH. That's pKw. Which of the following acids has the weakest conjugate base? Here's what you can think about. If something has a weak conjugate base, what's true about its conjugate acid? Is it stronger or weaker? Stronger. So, look at these 5 choices. Which of the 5 choices is the strongest acid listed? And again, you have to dig in your memory a little bit about this. Which of these would we consider to be a strong acid based on the criteria that we set down at the beginning of this chapter, where we listed out 7 strong acids? So is that nitric acid? Yeah, that's nitrous acid. Yeah, so HI is the one that fits because it is the strongest of these acids. All right. Whereas HF is probably well, I don't know about that. Actually, I think nitrous acid might be stronger than HF. Okay. But the problem you have, and this is something I've seen before when I've asked this question, is that students say, well, we don't have the tables we need to figure this out. Okay. And that's something you can think about. You say, oh, well, I really couldn't answer this question without the tables. But then you have to think, okay, all of these are weak acids except for HI. Okay. And the way the question is phrased, strongest conjugate base, that would be much more difficult. And actually, I wouldn't think it would be a reasonable question if I were to ask which of these has the strongest conjugate base, because you don't know the relative strengths of these weak acids. Okay, that's not something I've asked you to memorize, nor do I expect you to memorize. All right. If that were the case, though, the answer would be E, because hypochlorous acid is the weakest of these acids. Again, that's something I remember. It's not something I expect you to remember. Okay. So here's what we want to do. We know that a weak monoprotic acid, a 10th molar solution of a weak monoprotic acid has a pH of 3.50 at 25 degrees Celsius, and we want to calculate what is the Ka for this weak acid. See what you can do with that. I think that's the last question we're going to do this afternoon. So how did we do with this one? Got 3 of 6 answering. Oh, all over the place. Okay. I look at this. The concentration of hydrogen ion is 10 raised to the negative 3.50 molar. That's also equal to the concentration of the conjugate base. If I multiply those two numbers together, I get 10 raised to the negative 7th. The concentration of the conjugate acid is going to be 0.1 minus whatever that value is, which rounds back to 0.1. So I get 0.10. So I'm going to take 10 to the negative 7th divided by 0.10, and that gives me 1.0 times 10 to the negative 6th. All right, so you can see how that works. And again, that's something I think you definitely want to be prepared to do when you take the final next week. All right. I think that's a good place to stop. I'll have to remember to pick up on question 7 the next time we meet. There are a couple of other things you want to keep in mind. You do have an exam coming up on Wednesday. All right. That exam covers chapters 18 and 19. All right. So again, what you can think about with regard to the exam is you definitely want to look at those 2 worksheets that we've spent time on in class last time we met. And also you want to look at a number of other things. Okay. Look at the learning objectives for the chapter. That would do you well. All right, those kinds of things. Are there any questions I can answer before we split up this afternoon? Either with regard to the exam or with regard to the final. All right. So remember, tomorrow I will be around on campus. I'm going to be busy giving lab exams all day. And the same will be true Wednesday morning. But if you have questions, probably the safest way to reach out is to send me an email. Okay, because I will check my email periodically throughout the day. All right. If you need some kind of special attention where you need to answer a question face to face, I can set up a Zoom, but it probably wouldn't be till tomorrow evening after dinner sometime. I'm happy to do that if it would be helpful.